Hello, we are now on the last part of our lecture in Fundamentals of Engineering Mathematics. Here in Solid Geometry, we will be dealing here with figures in three-dimensional space. So unlike in plane geometry, where our concern is to solve problems of figures in two-dimensional, so here in Solid Geometry, the objects are in 3D. So let's start. First, let's discuss about solids for which the volume is equals to the area of base times the altitude. One example of which is the prism. Prism is a polyhedron in which two faces are equal polygons in parallel planes, and all other faces are parallelograms. So here are the examples of a prism. We have a rectangular prism, a hexagonal prism, triangular prism. So we have two faces parallel, and all other faces are also polygon. So we have here two face parallel for this hexagonal prism, and all other faces are also polygon. So what is the formula in computing the volume? So we have here two prisms. This one is an oblique prism, and the other one is a right prism. So as you can see, a right prism is where the base has perpendicular lateral sides or lateral faces. Unlike here, an oblique prism, we have an angle of inclination of the lateral faces of the base. So with respect to the base, so this corners here, or this lateral side, is not perpendicular to the base. So in order for us to compute the volume of an oblique prism, we need this perpendicular face, or the perpendicular area or perpendicular cross-sectional area with respect to the faces or to the lateral faces of the prism. Then multiply it to the length of the lateral side. For a right prism, just multiply the area of the base to the perpendicular distance or perpendicular height or altitude of that prism, which is h. For the lateral area or the area of the lateral faces of the prism, just multiply the perimeter of the base for the right prism, or the perimeter of this shaded region or the cross section of this one on the oblique prism to the lateral side. Okay, the length of the lateral side of that oblique prism. Same way here with the right prism, just multiply the perimeter or the perimeter of the base to the height. That's your lateral face or the surface area along the lateral faces. So if it is required here to determine the total surface area of the prism, just add the lateral face to the sum of the bases, which is twice the area of the base. Okay, for right truncated prism, um, if the lateral sides are not of equal length, which represents here as h1, h2, h3, in order for us to compute the volume of this truncated prism, We divide the area of the base by the number of sides of the base, which is this one, this one, that one, which means if this is a triangular prism, triangular truncated prism, we have a total of n, which is 3. Then multiply it to the sum of all the height from the vertex of the base. So in other words, take the average, okay, take the average of all the altitudes of this right truncated prism and multiply it to the area of the base. Okay. For the lateral area, just determine the area of these trapezoids formed by the lateral faces. Okay. So manually compute using the area of trapezoids. Next, let's answer this example. The side of the base of a regular hexagonal prism is 6 centimeters and its bases are 12 centimeters apart. Find its volume in cubic centimeters, lateral area in square centimeters, and the total surface area in square centimeters. So this is a regular hexagonal prism. So let's answer that. Okay, so here's the figure. If we have a hexagonal prism with a base of 8 centimeters, so if this is the base here, this is the cross-sectional base or the base, hexagon base. We have a side of 8 centimeters. Its bases are 12 centimeters apart, so we have an h of 12 centimeters. Determine A, the volume first. So since this is just a hexagonal prism, a regular hexagonal prism, we can simply apply the formula V equals to area of the base times the altitude. So let's find first the area of the base. So this is the base here. So let's just take one part of this regular hexagon by connecting the vertices to the center where we can form an isosceles triangle. Now, when we determine the central angle of that uh, triangle, which is 360 degrees, or just divide 360 degrees because that's the total angle of one revolution of, of angle from the center. Divide that by 6 since we have 6 parts here, 6 equal parts in terms of central angle. So we have an angle of 60 degrees. So if this is 60 degrees, it is expected that the other two angles are the same since this is an isosceles uh, triangle. Now, 180 divided by this angle here, theta. So let's assign theta, 2 theta, and subtract 60 degrees. It should be equals to 0 when we add these three angles. 2 theta and 60 should be 180 degrees. So to find theta, just subtract 180 by 60 and divide it by 2. So theta is equals to 60 degrees, which means this is an equilateral triangle. So this triangle is an equilateral triangle, is one, which means all of the sides are equal also. So if their interior angles are equal, their opposite sides are also equal. So that's 8 centimeters, 8 centimeters. To compute the area of the base, just compute the area of a single triangle and multiply that by 6. So for the area of the base, uh, going back here, the area of the base is 6 times 1 half AB sine theta. Okay, area of a triangle given two sides and included angle. So 8 times 8 sine 60 degrees. So the included angle is 60. Okay, area of the base is equals to 6 times 1 half times 8 times 8 times sine 60 degrees. So let's compute that. We have 166.277 square centimeter. Okay. Then multiply that area of the base to the altitude h. H is 12. 12. Okay. We have volume of 1995.322 cubic centimeters. Okay, next, find the lateral area. For letter B, the lateral area is equals to the perimeter of the base times h. So the perimeter, if we have one side equal to 8 centimeters, just multiply that by the 6 sides. So 8 times 6 divided by 6 and times the altitude 12. Okay, 12 centimeters. Okay, we have 576 square centimeters. That's your lateral area, or the area of the lateral faces or the sides of this hexagonal prism. Thirdly, what is the total surface area? Total surface area. For the total surface area, area total equals to the lateral area times twice the area of the base. So 576 plus 2 times 166.277. Okay, the area total is equals to 908.554 square centimeters. So that's the total surface area of this hexagonal prism. Okay, let's proceed to the next problem. Determine the volume of a right truncated prism with the following dimensions. Let the corner of the triangular base be defined by A, B, and C. The length AB is 10 feet, BC is 9 feet, and CA is 12 feet. The sides A, B, and C are perpendicular to the triangular base and have the height of 8.6 feet, 7.1 feet, and 5.5 feet respectively. So let's determine the volume. First, draw the figure, draw the solid, and here it is. We have 8.6 feet, 7.1 feet altitude, and 5.5 feet. So these are the length of perpendicular uh, or the sides perpendicular to the vertex of the base A, B, C. So given here, the length of sides of the bases 10 feet, 12 feet, and 9 feet. So this is a truncated prism. So the solution is the volume is equals to the area of the base divided by the number of sides times the sum of the sides A, B, and C, or the perpendicular sides with respect to the vertex of the base, or the altitudes of each sides. So we have H1, H2, and H3. So H1, H2, H3. Let's assign H1 here, H2, H3. First, determine the area of the base. This is the base here, which is a triangle with the given length of sides. So all sides are given. We can use Heron's formula. So using Heron's formula, the area of the base is just equals to the square root of S times S minus A, S minus B, S minus C, where S is the semi-perimeter, or the sum of all the sides divided by 2. Okay. So the semi-perimeter is 15.5 when we compute that. Now substitute that here. The area of the base is equals to 15.5 times 15.5 minus 9, 15.5 minus 10, 15.5 minus 12. The area of the base is equals to 44.039 square feet. Now, using again the formula here, the volume is equals to the area of the base, which is 44.039, divided by n, or the number of sides of the base, which is 3, and the sum of all the h. So h1 8.6, h2 7.1, h3 5.5. So the volume is 311.209 cubic feet. Okay. Now let's discuss another type of prism, which is the cube and rectangular parallelepiped. So they are also called as common prisms. Starting here on the cube, cube is also called as a regular hexahedron. Okay, a regular hexahedron, it is a polyhedron which 6 faces are all squares, or all of these faces are equal. All are equal. So that's a cube. All sides are equal, all faces are equal. Now, what are the formulas that we can use in computing the volume, area, diagonal, and space diagonal? For the volume, we have area of the base times the height. Okay, so if we assign A on one side with all other dimensions, just multiply the length, the width, and the height, which is equivalent to the A cube. For the area, surface area, total surface area of the cube, just compute the area of one face. So length times width, A times A. We have A squared, and multiply it to the number of sides, which is 6. For the face diagonal D, the face diagonal here is this one. So if we choose one face, okay, if we choose one face and we take the diagonal of of that face. This one is the face diagonal. So this formula is just derived from taking or using a right triangle form by this face. So if this is A, this is A. So this face diagonal is just the hypotenuse of this right triangle. So D squared is equals to A squared is A squared. So D is equals to the square root of 2A squared. So therefore D is A, the square root of 2. That's the face diagonal. And for the space diagonal, we have A the square root of 3. So this is the space diagonal from one corner to the other that is not of the same face. So we consider here three dimension, three-dimensional um, right triangle. So considering again this right triangle here, okay, we can solve this space diagonal. So before solving this S here, compute first this face diagonal, which is D, which is A the square root of 2. So if this is A the square root of 2, then take again Pythagorean theorem, S squared equals to A squared, because S is the hypotenuse. And the other one is A the square root of 2. So take the square of that also. Then compute S. So you have S square root of A squared plus um, 2A squared. So S equals to the square root of 3A squared or A the square root of 3. That's your space diagonal. For a rectangular parallelepiped, so rectangular parallelepiped is just all faces of a rectangular parallelepiped are rectangles and the two opposite faces are equal rectangles. So we have two equal faces, two equal opposite faces that are rectangle, and we have other four equal rectangles, which is this side, all of this lateral sides. So same formula applies in deriving the solution of the volume, the surface area, the face diagonals, and the space diagonal. We just use Pythagorean theorem by forming right triangles along this solid. So for the volume, we have this formula A times B times C, or the length times width times height. The total surface area, just compute the area of all the lateral faces and the other two opposite faces. And we have the diagonals. You can compute that using this formula or just use again the principles of Pythagorean theorem. And we have here the space diagonals. So same solution applies. So actually we need not to memorize these formulas as long as we know the uh, how to use the Pythagorean theorem in computing the diagonals. So let's answer some problems. A cube has a side of 6 centimeters. Determine the volume in cubic centimeters, total surface area, face diagonal, and space diagonal. So I think we need not to draw this. We can simply use the formula, or we can directly solve the problem by assigning A by 6 centimeters. So for the volume, volume is a cube. So 6 centimeters raised to 3 is 216 cubic centimeters. For the total surface area, 6a squared. The surface area is 6a squared. So 6 times 6 centimeters raised to 2. So when you compute that, that's 216 square centimeters also. Okay. For face diagonal, uh, the face diagonal D is a the square root of 2. So substitute again a by 6. So 6 the square root of 2, or that's 8.485 centimeters. And for S, we have a the square root of 3. 6 the square root of 3 is equivalent to 10.392 centimeters. These are the answers. Okay. Another example, the face diagonal of a cube is 4 the square root of 3. Find its volume. So given here, the face diagonal D. So recalling the formula for the face diagonal, which is a the square root of 2. Given the face diagonal, we'll be able to determine the uh, length of one side of the cube, or the length of side of the cube. So substitute D for the square root of 3. Then we have a the square root of 2. Divide both sides by the square root of 2. So that we'll be able to determine A. So we have an answer of 4 the square root of 3 over the square root of 2. We take the decimal form of that. Um, that is equivalent to 4.899 meters for the length of side. For the volume, have volume V equals to 4.899. We raise that to 3 because volume is A cubed. So 4.899 is 117.577 cubic meters. That's the answer. Okay. Another example for rectangular parallelepiped. A rectangular bin 4 feet long, 3 feet wide, and 2 feet high is solidly packed with bricks whose dimensions are 8 inches, 4 inches, 2 inches. The number of bricks in the bin is. So to compute the number of bricks in the bin, so if we have a bin here, first compute the total volume of the bin, then we divide that to the volume of a single brick. Okay, that way we will be able to determine the total number of bricks. Since we have a unit of feet on the rectangular bin and inches for the brick, we must be consistent on the unit that we will use before we apply it in this formula. So let's say we use feet on all the computations that we will use. So it means that we must convert these dimensions into feet. So converting inches to feet, just divide it by 12 in order for it to have a unit of feet. So this one would be 4 over 12 feet. 2 divided by 12 will be in feet. So we can now compute the number of bricks. First, the volume of the bin, given dimensions, length, width, and height. So L, length times width times height. That's the volume of that rectangular bin. So we have 4 feet times 3 feet times 2 feet. be divided by is 8 over 12 feet, 4 over 12 feet, 2 over 12. Okay, so we can directly solve that. Let's say the volume for the bead is 24 cubic feet. For the brick, when we compute that, we have 1 over 27 cubic feet. So divide that, we will have 648. So that's the number of bricks for this rectangular beam. Okay, another example, we have a packing box with dimensions 2 feet by 5 feet by 5.5 feet, completely covered with tin. How many square feet of the metal are needed, and what is the volume capacity of the packing box? Okay, so say this is the box. Okay. So we have sides A 2 feet, B 5 feet, and C 5.5. For the surface area A, because it will be completely covered with tin, so we need the total surface area uh, of this box. So for the surface area, we can use the formula that I presented earlier of 2 times AB plus BC plus C. Or you can just simply manually compute all of the lateral faces or all of the faces of this box, since all the dimensions are given, and add it. Okay, so we have here 2 times 2 times 5 plus 5 times 5.5 plus 2 times 5.5. Okay, computing that, we have a surface area, total surface area of 97 square feet. For the volume capacity, just multiply the length, width, and height. 2 feet, 5 feet, and 5.5 feet. We have total volume of 55.0 cubic feet. Okay, next, the cylinder. So it's also part of the solids, which volume is equals to the area of the base times the altitude. So still here in cylinders, uh, that formula is also still applicable, which is the area of the base is just to be multiplied by the height. Okay, so the only difference in cylinder is that the base, okay, cylinder is just a solid bounded by a closed cylindrical surface, and it has two parallel planes also. So here in cylinder, uh, most of the time we use a base of circle. Sometimes we ellipse is also used in a cylinder for the base, but um, the typical the typical solid, or the typical base that is always used when we say cylinder, is a circle. So again, applying the formula for the volume, area of the base times height, and for an oblique cylinder, this is the equivalent formula, and same applies with the lateral area, the perimeter of the base. So usually if it is circle, just the circumference of the base, times the length or the height. So again, let's solve some sample problems. An oblique circular cylinder has a lateral side with a length of 40 meters. If the base has a diameter of 4 meters and the lateral edge is inclined by 60 degrees with the horizontal, determine the volume of the cylinder. Okay, so this problem, we have a lateral edge inclined by 60 degrees, which means it is an oblique cylinder. So let's draw that. Okay, so here's the figure for this problem. We have a cylinder, circular cylinder, with a lateral side with a length of 40, right here, 40 meters. So, um, the base has a diameter of 4 meters, and this is the angle of inclination of the lateral edge or the lateral side, 60 degrees with respect to the horizontal. Now, determine the volume of the cylinder. In determining the volume of the cylinder, we can use uh, the formula area volume is equals to AR times L. We can use that. Or we can use area of the base times the altitude H. So here, what we only need if we are going to use this formula, which is the easier one, uh, we only need the value of the altitude H. Since given here is the length of lateral side, so the altitude is just the perpendicular distance between, or the parallel distance between the bases. So from this base to here, perpendicular from that base going downward. Okay, so this is the parallel distance between the bases. Okay, so if this is H here, we can form a right triangle again, and our hypotenuse is this lateral side, 40 meters. So given an angle of inclination of 60 degrees, we can use sine function. Okay, using sine function, we can determine h. Sine 60 is equals to the opposite h over the hypotenuse L. So record this h. Okay, we multiply both sides by L. We have L sine 60 degrees equals to h. Substitute 40 sine 60 equals to h. Therefore, h is 34.641 meters. That's your h here. Then, for the volume, you can now compute the volume using this formula. Area of the base times height. The area of the base is just the area of the circle. Area of the circular base given diameter, you can use pi d squared over 4 multiplied by h. So substitute 4 squared over 4 times h, 34.641. We have a volume of, computing that, we have 435.312 square, sorry, cubic meter. That's in cubic meter. Okay, next problem. A circular cylinder with a volume of 6.54 cubic meter is circumscribed about a right prism whose base is an equilateral triangle of side 1.25 meters. What is the altitude of the cylinder in meters? So let's draw that. Oh, so here's the figure for that. We have a circular cylinder circumscribed about a right prism. So we have a triangular prism inside a cylinder. Okay. So given the sides of the base of the equilateral triangle of the triangular prism, which is equivalent to 1.25 meters. So this, this is the base of the prism and the cylinder. Okay, given an equilateral triangle, so all sides are equal. What would be the altitude of the cylinder in meters? What is the altitude of the cylinder in meters? So given volume of the cylinder, okay, given volume of cylinder, okay, that's 6.54 cubic meters. Okay, so if we have the volume of the cylinder using the formula for the volume of the cylinder, we have the area of the base times the height. Okay, so the area of the base times the height. We have uh, we need also r, okay, for the area of the base, the radius of the circle. So given 6.54 equals to pi r squared times h. H is required. So let's determine h. Divide both sides by pi r squared. So this is cancelled. 6.54 over pi r squared equals to h. So what is r? We have to determine what is r. Uh, to determine r, let's proceed here on the circumscribing circle on an equilateral triangle or the base of the two solids. So if you have a circumscribing circle along a triangle, um, the distance from the center to the vertex are equal. Okay, they are equal, and that is the radius of the circumscribing circle. Okay, because the location of the center of a circumscribing circle on a triangle is called the circumcenter. Now, this is radius. This radius r, and r. So how to compute r? We focus on a triangle form, okay, a smaller triangle form. Say this one, okay, this triangle here with two sides which are r and 1.25. So how to compute that? Um, since this is an equilateral triangle, it means that the central angles or the angles formed by dividing it by the radius of by dividing the triangle by the radius by the line of formed by the radius of the circle, so they are also equal. They are also is, is an equilateral triangle. This angle here say theta, this is equal here. Therefore, uh, we can use 360 degrees divided by the number of sides, which is 3. Since 360 degrees over 3 is equivalent to what? That's 120 degrees. Okay, because a total of 360 degrees, divide that into 3 equal parts, we have 120 degrees. Okay, and since the other sides of this triangle, let's erase this, focusing on this smaller triangle here, we have two sides that are equal, which are the radius of circle. This is an equilateral triangle, which means that uh, if these sides are equal, the opposite angles are also equal. So if this is 120 degrees, when you add two equal angles, it should be 180 degrees. So in theta is equal to 180 degrees minus 120 degrees. That's 2 theta equals to 60 degrees. Divide both sides by 2. We have 30 degrees on each side. Okay. Okay, let me use beta para, so that we don't have confusion. This is beta, beta. So 30 degrees here, 30 degrees right here. So uh, we we now have interior angles. Okay, let's redraw the triangle here. This one. We have 120 degrees, 30 degrees, 30 degrees, and this side 1.25. So we can use sine function in computing the radius here, or so using sine law, we take the ratio of the side with respect to the sine of that angle, of the opposite angle. So r divided by sine, the opposite angle of r, which is beta or 30 degrees, is equivalent to this side 1.25 over sine the opposite angle 120 degrees. Okay, so r is equals to 1.25 sine 30 degrees over sine 120 degrees. So r is equals to 0.722 meters. Going back to this formula here, we can now substitute r, which is 6.54 over pi r, or 0.722 squared. 722 squared equals to h. So h therefore is equals to 3.993 meters. That's the answer. Okay, next. So we come now to the solids for which volume is equals to 1/3 the area of base times the altitude. So these solids are cone and a pyramid. So let's discuss first the cone. We use the formula 1/3 area of the base times the height. Same applies with the pyramid. So as you can see here, if we have a right circular cone, when we unroll that cone, we form a sector of a circle. So if right here, if this is the lateral side of that right circular cone, or which is L, or the slant height, when we unroll that, That would be the equivalent radius of the sector, while the base circumference or the perimeter of the base, that will be equivalent to the length of arc of this sector of an unrolled cone. Okay, so again, the volume is 1/3 pi r squared h. 1/3 pi r squared is just the area of the base, area of a circle, and h is the altitude. And we have other relationship between r, h, and the lateral or the slant height L. So we just use the principle again of Pythagorean theorem. Since we form a right triangle here, we have r squared plus h squared equals to L squared. For the lateral area, pi RL is the solution. Okay. For the pyramid, for the total surface area, we have area of the base plus the lateral area, or the lateral area of pyramid, are these triangles form. Okay, all of these lateral faces, which are triangles. Then add the base for the total surface area. Same applies with cone. If it is required the total surface area, add the base to the lateral area. For the volume, area of the base times height, take the 1/3 of it. Okay, let's answer this example. Slant height of a right circular cone is 5 meters long. The base diameter is 6 meters. Determine the lateral area, the surface area, total surface area, and the volume of the cone. Okay, so if this is your cone here, okay, we have slant height 5, okay, L 5, and we have diameter as 6. Okay, so for the lateral area for A, we can simply apply pi r L. So what is r? If the diameter is 6, 1/2 of that, that's your radius. So 6 over 2 is 3 meters. That's your radius, r. So pi times 3 times the slant height L, which is 5. Okay, that's 15 pi, or 47.124 square meters. That's your lateral area. For the total surface area, just add the base. Okay, area total, area of the base, plus area of lateral. Okay, area of the base, we have ranges of 3. So pi r squared plus lateral area 47.124. So 47.124 add to pi 3 squared. We have total surface area of 75.398 square meter. For letter C, volume of the cone. Volume of the cone is 1/3 pi r squared h. We don't have the altitude yet. So if this is h, this is r. So Pythagorean theorem, L squared equals to h squared plus r squared. Determine h. So L squared minus r squared equals to h squared. Take the square root. So h is equals to the square root of L squared minus r squared. Oh, the square root of 5 squared minus 3 squared. Your h is, so I will directly compute that. We have 4. So substitute 1 half pi times, sorry, this is 3 squared times 4, 1/3. So the volume is 12 by 4 in decimal, 37.699 cubic meter. Okay, next. The axis of a cone is inclined at an angle of 80 degrees with the horizontal. Compute the volume of the cone if its axis is 30 centimeters long and its base diameter is 20 centimeters. So let's draw the figure. Okay, so we have an axis of 30 centimeters long. This is 30 centimeters. This is the axis from the center to the vertex of the cone. Then we have a diameter of 20. Okay, and an angle of inclination of 80 degrees. So in solving the volume of a cone, we have 1/3 area of the base times side. So we must compute the height or the altitude of this cone. So say we have a line here from the vertex. Okay, sorry. Okay, say here we have a line here, and we have a line here from the center can form a right triangle, since uh, the altitude is the perpendicular distance from the base of the cone to the vertex. So we form a right triangle. Uh, if this is h here, we can apply again sine function. Okay, sine function, sine 80 degrees equals to the opposite side h over 30. Therefore, multiplying both sides by 30, we have 30 sine 80 degrees equals to h. Okay, computing that, h is 29.544 centimeters. So we can now compute the volume of the cone, where the area of the base is for the area of circle given diameter. So pi d squared over 4 times h. Substitute diameter, pi, that's 20 square over 4. Okay, h is 29.544. The volume therefore is equals to 3093. Okay, 0.84 cubic centimeters. So all the units are consistent on the axis and the diameter. So that's cubic centimeters. That's the volume. 3093.84. Okay, next problem. The next problem is a right circular cone was formed by rolling a thin sheet of metal in the form of a sector of a circle 72 centimeters in diameter with a central angle of 150 degrees. Find the volume of the cone. Okay, so let's draw the figure. So here is your sector here that we will use to form a right circular cone. It's given there that the diameter of the sector is 72 centimeters. So if that is the diameter, uh, we need the radius, which is the diameter is one of the diameter is the radius. Taking half of 72, that's 36 degrees at 36 centimeters. So that will be your equivalent slant height of your cone here, and that's the radius of the sector, 36 centimeters. While we have a central angle of 150 degrees. Find the volume of the cone. So in finding the volume of the cone, this cone here, okay, we need the radius and the altitude because one third of the area of the base times the height. The area of the base is area of the circle pi r squared times h. So we don't have yet h in the radius of the circle, which is the base of the cone. So the radius here on the sector, that's not the radius that we will use here because the equivalent radius of the sector is the slant height of the cone. So uh, what we will use here is that we will make an equation equating the circumference of the base, which is right here, is the circle here. We will equate that to the length of arc of the sector, okay, because they are equal. The length of the base when the sector is rho, okay, this will be the equivalent base, the equivalent circumference of the base of the cone. So equating the two, we have here length of arc of sector, which is sector, is equivalent to the circumference of base of the right circular cone. Equating the two, uh, formula for the length of arc, that's uh, pi r theta. Okay, so our r here is the radius of the sector, so instead of using r, we use l. Okay, so that uh, if I'm confused, we will not be confused on what radius we will use. So we are concerned here with the sector, so what radius we will use here on the sector is the radius of the sector. So pi ri, which is theta, the central angle, over 180. That's the length of arc of a sector. Equate to the circumference of the base or circumference of the circle. Now this is your radius r. That's 2 pi r. Okay. So L is given, R is unknown. Theta is also given. We can determine R. Okay. So let's compute. Pi 36 theta 150 degrees divided by 180 degrees is equals to 2 pi. Divide both sides by 2 pi to determine R. We have 36 150 over 2 pi times 180 degrees. Okay, so evaluate this equation. Within that, pi times 36 times 150 over 2 pi. Now your radius is 15 centimeters. Okay, we have a radius, but we don't have the altitude h. To compute h, given r, which is 15, using again Pythagorean theorem, L squared h squared plus r squared. So we can determine h. Evaluating that equation, we have h equals to L squared minus r squared. So h equals to 36 squared minus 15 squared. Your h is 32.726. So we have now h, we have now r. We can now compute the volume. Okay, so the volume of a cone, 1/3 by r squared h. So 1/3 by 15 squared. H is 32.726. Volume therefore is 7710.882 cubic centimeters. That's the final answer. Okay, we're done with sample problems with cone. We now proceed to pyramids. So the problem is a regular hexagonal pyramid whose perimeter is 60 centimeters has an altitude of 30 centimeters. Determine the volume of the pyramid and the total surface area. So let's draw that. So here's the figure. We have a pyramid, hexagonal pyramid. We have an altitude of 30 centimeters with a given perimeter of 60 centimeters. Since it is a regular hexagonal pyramid, so if this is the base, which is a hexagon, okay, we just equally divide the sides by the number of sides. So we divide the perimeter by the number of sides of the base. So if this is a six-sided polygon, we have perimeter divided by 6. So each side is uh, 10 centimeters. So I will assign here a 10 centimeters. Now, connecting again the vertices of the hexagon to the center of the hexagon. Let's form again a triangle because that will be useful in determining the area of the base. So we determine the area of this triangle formed here, and let's just multiply it by 6 because we have 6 sides. Okay, so the central angle here is equivalent to what? If we have a total angle of 360 degrees, 360 degrees divided by 6 is 60. So that's your central angle for this triangle. And since this is a regular hexagon, these sides are equal. Okay, so more likely in a regular hexagon, this triangle formed here is always equilateral. Okay, since the remaining angles equals 220 degrees and dividing it equally, dividing it by 2, that's 60 degrees. So if all the interior angles are 60 degrees, which means that all the sides of the triangle are 10 centimeters. Okay, it's 10 centimeters, 10 centimeters. We can compute now the volume of the pyramid. Okay, So first, compute the area of the base, 6 times uh, the area of a single triangle, 1/2 AB, two sides, 10, 10, and included angle 60 degrees. 60 degrees. Okay, the area of the base is 259.808 square centimeters. Okay, so for A, the volume of pyramid is equals to V, one third area of the base times height. One third area of the base, 259.808. The height is 30. Okay, so we are consistent in centimeters units. So the volume therefore is 2598.0 cubic centimeters. So this is your volume. Next, for the total surface area. So for the surface area, um, we have to determine the area of a lateral side. Since this is a regular hexagonal pyramid, it means that all of the triangles on a lateral surface of this pyramid are equal. So let's just determine a lateral side or a lateral surface on a single side, then multiply it by 6. So how can we determine this area here? Okay, so the triangle formed here is an isosceles triangle where we have two sides equal, and this side is 10. Okay, so it is not possible for us to determine the area since we don't know this dimension here, this distance x here from the vertex of the hexagon, the vertex of the pyramid. Okay, so let's determine that x first. So how can we determine that x? So if we have an altitude here, going to the center of the base, this is your altitude here, and we connect that point where the center of the hexagonal base, we connect that to the vertex of the base right here. Okay, we can form again a right triangle, which is this one, right? This triangle here, here, here. Okay, so this distance here from center to the vertex going back to the base is just the same as this one, or any of this line here from the center going to the vertex. So this is also, so if we already know that it is 10, this is also 10 centimeters. So using this triangle, this right triangle, we can solve x. And since we know this distance here, this is the altitude h, which is 30 centimeters. So focusing on the triangle, we have h 30 or 10, we can determine x. And after that, we will now focus on the lateral side, which both sides are x, and another side which is 10 centimeters. So let's focus first on this triangle here. Okay, this triangle here. So this is on this triangle. Okay, so focusing on this triangle, we have the right triangle. Okay, using Pythagorean theorem, x squared equals to h squared plus r squared. So x equals to the square root of h squared plus r squared. So the square root of h squared, 30 squared, it's 10 squared. That's x. So x is equals to 31.623 square centimeter. So after determining x, can now focus on this triangle, which is this one. So any lateral face of this pyramid, you can use this. That's your area. Okay, just determine the area. Both sides are x, and this is 10. So we focus on the triangle. This is the triangle, the lateral side. Okay, so let's determine the area. Let's say area 1. Area 1, if we have x here, all sides are given, we can use Heron's formula, which is s times s minus a, s minus b, s minus c. So the semi-perimeter is a plus b plus c over 2, or 10 plus the two sides x, 31.623 plus 31.623 over 2. So s is equals to 36.623. Okay, substitute that here for the area. 36.623, 36.623 minus 8 and 36.623 minus 31.623, 36.623 minus 31.623. Okay, so computing all that, we have an area of 156.126 square centimeters. Okay, that's the area of one side only. So the total lateral area is 156.126 multiplied by 6 sides. So that is equals to 936.756 square centimeters. So what is required here is the total surface area. So total surface area is area of the base plus area lateral. The area of the base already determined earlier. We have 259.808, 259.808 plus 936.756. The total surface area is 1196.564 square centimeters. That's the answer. Okay, so we're done with cones and pyramids. Let's now proceed. For frustum, a frustum of a pyramid or a cone is a portion of pyramid or the cone included between the base and the section parallel to the base, not passing through the vertex. So a frustum is just a part of a pyramid or a cone where we have two bases which are parallel. Okay, so the volume for frustum, we have formula of h over 3, where h is the altitude, times area 1 plus area 2 plus the square root of area 1 and area 2. So area 1 and area 2 are the area of the bases of the frustum of a cone or a pyramid. Okay, so additional formula if we want to determine the lateral surface So actually, we can manually compute the lateral surface of a uh, frustum of a cone. Okay, so for the frustum of a cone, the lateral area is pi r plus r gross quantity, the square root of r minus r squared plus h squared. So this is the derived formula in determining the lateral surface area. But uh, the manual solution for that is we determine the whole lateral surface area of the cone, then we reduce that surface area not included for the frustum. So let's proceed on the example. A frustum of pyramid has an upper base of 100 meter by 10 meters and a lower base of 80 meter by 8 meters. If the altitude of the frustum is 5 meters, find its volume. Okay, okay. So let's say the lower base is 100 by 10 and the upper base is 80 by 8. Okay. Determine the volume of this frustum of a pyramid with an h or altitude of 5 meters. So by simply applying the formula for the volume of a frustum, okay, volume is just h over 3 times area 1 plus area 2 plus the square root of the product of the areas. So determining first the areas, area 1, let's say this is area 1, this is area 2, 80 times 8, you have 640 square meter, area 2, 100 times 10, that's 1000 square meter. So substitute 5 over 3, 640 plus 1000 plus the square root of 640 times 1000. Okay, so the volume is 4066.667 square meter. Okay, for the next problem, we have a frustum of a cone having an upper base radius of 5 and the lower base radius of 7. The altitude is 11, determine the volume, and B, the lateral area of the frustum. So what are the given? Radius of the upper 5 meters, lower is 7, h is 11. For letter A, the volume is equals to h of 3, area 1 plus area 2 plus the square root of area 1, area 2. Find the area. Area 1 is pi r squared, pi 5 squared, that's 78.54 square meter. For area 2, pi r squared also, pi 7 squared, that's 153.94. For the volume, substitute all the given 11 over 3, 78.54 plus 153.94 plus the square root of product of the areas 153.94. The volume is 1255.601 cubic meters. Okay, what is the lateral surface area? That's the volume. For B, lateral surface area. So this is the formula, r plus r square root of r minus r squared plus h squared. Okay, Direct substitution, 5 plus 7 square root of 7 minus 5 square plus 11 square. Lateral area is 421.489 square meter. Okay, that's the lateral area of the frustum of a cone. Okay, next, for sphere. A sphere is a solid bounded by a closed surface, every point of which is equidistant from a fixed point, which is the center. Now, here are the formulas that we can use in determining the surface area. We have 4 pi r squared or pi d squared. For the volume, we have 4 third pi r cubed and 1/6 pi d cubed. For a spherical segment is a solid bounded by one or two parallel planes through a sphere. So we take just one part or a part of a sphere by plane, either one plane, which is this one, spherical segment with one base, and if we have two parallel planes cutting the sphere, we have a spherical segment with two bases. Now, what are the formula that we can use in determining the volume and area and the surface area of a spherical segment? For one base, for the volume, we have 1/3 pi h squared times 3r minus h for spherical segment with one base. For the area of the zone, or the lateral area or the surface area of the spherical segment, we have 2 pi rh. For spherical segment with two base, we have volume of 1/6 pi h times 3a squared plus 3b squared plus h squared. For the lateral area or the surface area, we have pi times a squared plus b squared plus 2rh. Okay, so let's solve this example. Let's compute first the volume of a sphere, which is 696.691 cubic centimeters. What will be the equivalent surface area of that sphere? So we have a given volume of the sphere. From the volume of the sphere, okay, 696.91. Using the formula for the volume of the sphere, we will be able to determine the radius. Okay, so substitute 696.91 for third pi r cubed. Okay, divide both sides or multiply both sides by 3 over 4 pi 3 over 4 pi to eliminate this pi and 3. So what remains is r cubed, and we have this one, multiply 3 over 4 pi by 696.91. We have 166.375. Take the cube root of both sides so that r remains. We have 5.5 centimeters. That's the radius of the sphere. Can I compute the surface area? The surface area is 4 pi r squared. Okay, so r is 5.5. The surface area is 380.133 square centimeters. That's the answer. Next problem. Uh, hemispherical bulb of radius 10 centimeters is filled with water to such depth that the water surface area is equals to 75 pi square centimeters. The volume of water is. So let's draw the figure. Okay, so let's say this is the hemispherical bulb. So if we have a radius of 10 centimeters and the water surface area equal to 75 pi square centimeters. So it's not said there that the hemispherical bulb is fully filled with water. So it is given there that it is filled at a certain depth that we don't know yet. But it is given there that the water surface area is 75 pi square centimeters. So let's say this is the surface of the water. So it means that the surface area of this is 75 pi square centimeters, or in top view, that's a circle. That's a circle. So the area of that is 75 uh, pi square centimeters. Okay. What is required is the volume of this water. Okay. So for the volume of a spherical segment, so this is spherical segment with one base. So the applicable formula is 1/3 pi h squared 3r minus h. So r here is the radius of the sphere. H is the altitude of the water, which is this one. So if we have a given radius of hemisphere or the sphere, which is 10, so if this is a hemispherical bulb, this is half of a sphere. So it means the total height here is also 10. So if we have a height h, okay, it means that this distance here is 10 minus h. So we need to compute h first. So in order for us to compute this height of water or the depth of water, all we need to do is we should form another right triangle by connecting the center of the hemisphere or of the sphere, or if this is a whole sphere, the center to any point or to the edge of the water surface, which is this one. So we will connect that here, and that distance from the center to any point of the sphere is also the radius, which is 10. So this is 10. And this distance here is the radius of the water surface. Okay. Since we have a given area of the water surface, we can determine this r here, small r, which means that's the radius of the surface of the water. And we have a vertical distance here from the center to the center of the water surface. That will be 10 minus h. So using this right triangle form here, we can compute h since all the dimensions can be determined and given. So let's say it's focusing on that triangle here. We have r, small r, 10, and 10 minus h. Okay, so to determine this r, focusing on this water surface, the area of the water surface is pi r squared. So water surface is 75 pi square centimeters equals to pi r squared. So divide both sides by pi. Okay, we have 75 r squared. Square both sides. We have a radius of 8.66 centimeters. That's the radius of the water surface. Okay, so we have a value here. Means if we will use Pythagorean theorem again, the only variable left is h. So we can now determine h. So Pythagorean theorem, hypotenuse times 10 minus h squared plus r squared. So what is required here is h. So 10 squared, 100, 10 minus h squared, or r squared is 8.66 squared. So, okay, I will transpose 8.66 squared on the left side of the equation, and I will extract this one. We will have 100 minus 20h plus h squared. Okay, so we have here uh, 25.0044 equals 100 minus 8.66 squared. Then we transpose 100 to the left side. We have minus 100 and negative 20h plus h squared. This will be negative 74.9956 equals to negative 20h plus h squared. Okay, so transpose again. We have 74.9956 minus 20h plus h squared, or arranging that equation, we have h squared minus 20h plus 74.9956 equals to 0. So this is a quadratic equation. So we use quadratic formula. So we have two possible value of h here. So your a here is 1, your b is negative 20, c is 74.9956. So let's apply quadratic formula. h1, h2, okay, negative b plus or minus the square root of b squared minus 4ac over 2a. So substitute all that. We have positive 20 plus or minus the square root of negative 20 squared minus 4, 1, 74.9956 all over 2 times 1. Okay, so uh, if I use positive, we have 15.06 centimeters. If I use negative, the computed h is 5.00 centimeters. So um, there are two possible value of h that we will use. There is only one possible value of h. It's either the 15 centimeters or the 5 centimeter. So basing on the drawing, okay, if the radius of the hemispherical bulb is 10 centimeters, it means if it is not fully filled, because the distance from the center at any point to any point of the sphere is 10, which is the radius. It means that if it is not fully filled, your height h should be less than 10. So basing on the two, the correct value of h that we will use here is this one, the 5 centimeters, because 15 centimeters, that's greater than the radius. So it means that the the water is overflowing on the hemispherical ball. So this is the correct h. This is the correct h. It means that, applying again the formula, which is 1/3 pi h squared 3r minus h, 1/3 pi h is 5 squared, 3 times 10 minus 5. Okay, that's the volume. 1/3 pi times 5 squared times 3 times 10 minus 5. So I'm directly computing that. We have a volume of 654.498 cubic centimeters. That's the volume of the water. So that's the solution for this problem. Next problem, a ball in the form of a spherical segment with two bases has a height of 0.1. The upper base is a great circle with a radius of 0.6. Compute the capacity of the ball. Okay, compute the volume. So this is a spherical segment with two bases. So here's the figure. We have a height of 0.1, okay, 0.1 meters. So the radius of the great circle, or if it is a whole sphere, that would be 0.6 meters. That is the volume of the ball. Okay. So the upper base is a great circle. It means that uh, the this is almost an equivalent of a hemisphere, because the upper base is a great circle, or the radius of that upper base is just equivalent to the radius of the sphere. Now, uh, how can we compute the radius of the other base, which is this one? Say this is A, this is B. How can we compute this other base so that we can determine the volume of this uh, bulb? So again, if this is the center of the base, we connect again the center of the great circle to any point of the sphere. So that distance is also equals to radius of the great circle. Now the vertical distance between the centers of the two is the altitude, which is 0.1. Then connecting the two, we form again a right triangle. So this is B, the radius of the lower base. This distance here is the radius of the great circle or the sphere, and this 0.1 here is the altitude. So from that we can compute B. Okay, so using that right triangle form, we have B 0.1, R. R is 0.6. Okay, by Pythagorean theorem, R squared 0.1 squared plus B squared. So E is equal to the square root of R squared minus 0.1 squared, where R, big R, is 0.6. Okay, directly computing that class, we're able to determine the B, which is 0.592. So since we already have the radius of the upper base and the lower base and the altitude, we can now apply the formula pi h over 6, 3e squared plus 3b squared plus h squared. So the volume is pi times 0.1 over 6 times 3 times 0.6 square plus 3 times 0.592 square plus 0.1 square. Okay, so the volume is equals to pi times 0.1 over 6. Putting all this one, putting this, we have 2.141, or the volume is 0.1121 cubic meters. Okay, that's the volume for a spherical segment with two bays. I come now to the spherical wedge and spherical loom. So spherical wedge is a solid form by revolving a semicircle about its diameter by less than 360 degrees, while the spherical loom, it is the curved surface of the wedge. It is the surface formed by revolving a semicircular arc about its diameter by less than 360 degrees. So here in spherical wedge and loom, we are required to have the radius and the central angle in order for us to solve the volume and the surface area. So for the wedge, what is required is the volume. This is the equivalent formula. 1 over 270 pi r cubed times theta in degrees. For loon, we have 1 over 90 pi r squared theta in degrees, or in radians, we have 2 r squared theta. Okay, so we have a spherical sector. It is also called as a spherical cone. So a spherical sector is a solid generated by revolving a sector of a circle about an axis which passes through the center of the circle, but which contains no point inside the sector. So here we have an H, we have the radius of the inner circle that is formed by the cone, or that it will be the base of the cone. So a spherical sector is just a combination of a cone and the spherical segment. So if we want to manually compute the volume of that, just determine the volume of the cone and this volume of the spherical segment. But if we want to directly compute the volume of a spherical sector given the height h r and the radius of the sphere r, we use this formula: v equals to 2/3 pi r squared h. Okay, so let's answer this problem. The volume of a spherical wedge is 172.8 cubic meters, and the area of its loom is 86.4. Find the radius of the sphere. Okay, so the solution for this problem, if we have a given of the volume of wedge, spherical wedge, we have 172.80 cubic meters, and the area of the loom, which is equals to 86.4 square meters. We are required to determine the radius of the sphere. So using the formula of the volume of the wedge, which is equals to pi over 270 r squared theta, should be in degrees, uh, we can determine theta by dividing the volume of wedge by uh, pi r squared, r squared, r cube, sorry, this r cube, and 270. Okay, that will be your theta. On the other hand, if we use the formula for the area of the loom, we have here pi r squared theta in degrees over 90. So let's determine also theta. Okay, theta here is what? We will just substitute the theta here to this formula on the area of the loon. So if the area of the loon, substituting the theta from the which we derive from the formula of the volume of the wedge, we have here theta is volume of the wedge times 270 over pi r cubed. Okay, so what is required here is the volume of the radius. So this will be cancelled out. What remains is r. So we multiply both sides by r in order for us to eliminate this, and we have to divide both sides by the area of the loop, so that on the left hand side of the equation what remains is the r. So we will cancel out. So r is equals to pi. Pi also is cancelled out. So what remains is 1 over 90 volume of wedge times 270 over area of the loop. Okay, so substitute all the given. We have here volume of the wedge, which is 172.8, and 270 degrees over 90 degrees. This is 86, area of loon 86.4. So multiply all that, we have an answer of 6 meters for the radius of the sphere. So that's the solution. Next problem. Find the volume of a spherical sector of altitude 3 centimeters and radius of 5 centimeters. So given h is 3, radius is 5, or big R. So solution, volume is 2/3 pi r squared h for the volume of spherical sector. So simply substituting all the given, have 5 centimeter square times 3 centimeter. Okay, you can easily determine the volume of the sector, which is 157.08 cubic centimeters. That ends our lecture in solid geometry. Thank you and God bless.